You know, the ground beneath your feet feels pretty solid, right? But it's not. It's moving, right now. And for the better part of a century, that simple idea was one of the most controversial in all of science. Today, we're going to dig into the incredible story of plate tectonics and how a completely ridiculed theory about wandering continents became the absolute bedrock of modern geology.
So think of this as a scientific detective story. It's all about a truly radical idea that entire continents could just drift across the face of the planet. An idea that was laughed at for decades until a few unexpected clues hidden in the deepest, darkest parts of the ocean changed absolutely everything.
Okay, so our story kicks off in the early 20th century, and it starts with a German meteorologist, of all people, named Alfred Wegener. And he had this completely audacious theory he called continental drift. It all began with a simple observation, one you've probably made yourself just looking at a map. The coastlines of South America and Africa look like they should just click together. Wegener saw that puzzle piece and just ran with it. He proposed that all the continents were once joined together in a massive supercontinent he named Pangaea, which eventually broke apart and drifted to where they are today. But here's the thing. This wasn't just some hunch based on a map. Wegener built an incredible case. He connected ancient mountain ranges, showing how the Appalachians lined up perfectly with mountains in Scotland. He pointed out that fossils of the exact same land-dwelling reptiles were being found on opposite sides of the Atlantic. How does that happen? And get this, he even found evidence of ancient glaciers in places that are now tropical. He was a meteorologist, arguing geology, using paleontology. It was completely revolutionary. So with all this evidence, you'd think everyone would be on board, right? Yeah, not so much. In fact, for decades, Wegener's idea faced some seriously fierce, and I mean hostile, opposition from the scientific community.
It really boiled down to a fundamental clash between two completely different views of the world. On one side, you had the fixists. They believed the continents were locked in place, and that any changes were just things moving up and down. To explain those weird fossils, they just imagined giant land bridges that had magically sunk into the sea. But Wegener's mobilist view was way more radical. He imagined a world of massive horizontal motion.
But look, as good as Wegener's evidence was, there was a fatal flaw, a huge one. He couldn't answer the single most important question. What kind of force could possibly be powerful enough to push an entire continent through the solid rock of the ocean floor?
And this is where the theory just hits a brick wall. The most prominent geophysicist of the day, Sir Harold Jeffreys, basically did the math. He calculated that no force we knew of, not the Earth's spin, not the tides, nothing, was even close to strong enough to do the job. And with that, Wegener's theory was, for all intents and purposes, dead in the water.
And for decades, that was pretty much that. But the solution, the key to the whole puzzle, was hiding in a place nobody had ever really seen before. The deep, dark, unexplored ocean floor. And it was technology from World War II that would finally let us see what was down there.
Then along comes a geologist named Harry Hess. In an essay he charmingly called Geopoetry, he laid out a brilliant solution. What if, he said, new ocean floor is constantly being created at these mid-ocean ridges? Magma comes up, cools, and then spreads outward. And this was the beautiful part. The continents don't have to plow through anything. They're just passengers, carried along on top of this giant planetary conveyor belt.
So how do you prove an idea that big? Well, the proof came from a really unexpected place: the Earth's magnetic field. See, scientists already knew that our planet's magnetic poles, north and south, flip every now and then. And here's the crucial part. When molten rock cools, the little magnetic minerals inside it lock into place, like tiny compass needles, recording the direction of the magnetic fields at that exact moment.
So as ships with magnetometers started mapping the ocean floor, this absolutely stunning pattern emerged. They found these perfect, symmetrical, zebra-like stripes of normal and reversed magnetism, mirrored exactly on both sides of the mid-ocean ridges. This was it. This was the smoking gun. It was undeniable proof that new crust was being born at the ridge and spreading outwards.
I mean, that quote says it all, right? The ocean floor was literally acting like a giant tape recorder, preserving a perfect magnetic history of its own creation. Suddenly, everything clicked. Wegener was right. The continents were moving, carried along by the very mechanism he was missing: seafloor spreading.
Okay, so now we know how the plates are moving, but the next big question is why?
What is the engine driving this massive planet-wide system?
Well, it turns out the main engine is just gravity. It's surprisingly simple, but incredibly powerful. As a slab of oceanic crust gets older and moves away from the ridge where it was born, it cools down and gets denser. Eventually, it gets so dense that it starts to sink back into the mantle under its own weight. And as that heavy slab sinks, it literally pulls the rest of the plate along behind it. That's slab pull. Now, there is also a little helper force called ridge push. Because the mid-ocean ridges are basically big underwater mountain ranges, they're sitting up high, so gravity gives the brand new plate a gentle little nudge, causing it to slide downhill away from the ridge. It helps, but it's not the main event.
And you can see right here, it's not even a close competition. Slab pull is the real powerhouse, doing about 90% of the work. Ridge push is just that extra 10%. And this is key. It totally explains why plates with huge subducting slabs, like the Pacific Plate, are the fastest moving plates on the planet.
All right, so let's fast forward to today. How does this all play out in the here and now? And maybe more importantly, what can it tell us about the future of our world?
The really cool thing is this isn't some abstract historical theory anymore. We can literally watch it happen. With technology like GPS, we can track plate motion in real time, down to the millimeter. For instance, Australia is cruising northeast at about 7 centimeters a year, which is, fun fact, about the same speed your fingernails grow.
And it's not just Australia, of course. We're tracking all the major plates, and the data perfectly confirms the model. You can see plates like the Pacific and Nazca, which have a lot of slab pull, are absolutely flying along. And then you have plates like the Eurasian plate, which doesn't have much subduction going on and it's barely crawling. It all fits.
What's really wild to think about is that this has all happened before, and it's going to happen again. Geologists have figured out there's this grand supercontinent cycle of continents crashing together and ripping apart that goes back billions of years. We've had Rodinia, Pangaea, and of course Pangaea. The cycle is still going.
So, what's the next supercontinent gonna look like? Well, there are a couple of competing theories. One idea, called Pangaea Proxima, suggests the Atlantic will close up, smashing the Americas back into Africa and Eurasia. Another, called Amazia, predicts the Pacific Ocean will disappear, pulling North America and Asia together over the North Pole.
And that brings us to one final, pretty provocative thought. The very same tectonic engine that creates our dynamic, life-sustaining planet could, in the deep future, create a world hostile to that life. Climate models for the next supercontinent predict a brutal planet with vast, scorching deserts. It's a powerful reminder that the only constant on our planet is change. Our world is, and always will be, a planet in motion.